You know, whenever I hear silicon, my brain goes to one of two places.
Okay.
I'm either picturing tech bros in fleece vests down in the valley, or I'm thinking about sand.
Just plain old sand.
Exactly. Just get in your swimsuit and never leave. Beach sand.
Well, that's entirely fair. I mean, considering silicon makes up more than a quarter of the Earth's crust, sand is definitely its most common form. It's the reliable, maybe a little boring backdrop to our planet.
Right. It's the background character of the periodic table. Useful, but not thrilling. But then, every once in a while, I'll watch an old Star Trek episode, that one with the Horda.
Oh, yeah, the silicon-based life form.
The blob monster. And I think, could that actually happen? Like, could a rock actually be alive?
Ah, the classic sci-fi trope. It's a favorite for writers, but usually a bit of a headache for chemists.
Right. And normally I just write it off as Hollywood magic, but today feels like we're inching just a tiny bit closer. Welcome, everyone, to the Deep Dive Lab.
We're looking at a brand new paper that basically forces a rock to act a little bit more like a living thing.
And it's a study that really challenges the fundamental rules of chemistry. We're diving into a paper from the journal Science.
But you know it's the real deal.
Titled Silicon Cyclopentadienes, featuring a nonplanar 6-aromatic C5 ring.
It's a mouthful.
Okay, that is a dense title. But our mission for this deep dive is simple. We're going to explain how a team from Tohoku University in Japan broke a rule that has frustrated scientists for decades.
And this isn't just about mixing chemicals. This is really about identity. It's about taking an element, silicon, and forcing it to behave in a way that just goes against its very nature. The authors, Takeaki Iwamoto, Tomoki Ishikawa, and Shintaro Ishida, they basically taught a fish to climb a tree.
I love that. And the fish they taught is a silicon cyclopentadiene. Okay, we have to unpack that immediately. It sounds like a spell from Harry Potter.
It does have a certain wizardly ring to it, yeah.
Cyclopentadiene.
Simply put, they made a ring of 5 silicon atoms, and they got those atoms to share electrons in this very specific flowing way.
A way that until now was pretty much just a carbon thing.
Exactly. It was carbon's trademark.
So silicon is trying to impersonate its cooler, more popular younger brother.
That is actually the perfect way to frame it. To really get why this is such a big deal, you have to look at this. Family rivalry.
Okay.
Carbon and silicon, they both live in group 14 of the periodic table. They're siblings.
But with very different vibes. Like they're in the same family, but they are not the same person at all.
Drastically different. Think of carbon as the extroverted gymnast of the family.
The gymnast, I like that.
It's flexible. It loves to bond with everything. It makes life, DNA, plastics, fuels, and crucially, carbon loves making double and triple bonds. It can form these flat, beautiful rings where electrons just dance around.
Right, like those benzene rings from high school chemistry, the little hexagons.
Exactly those.
Yeah.
Carbon is totally comfortable being flat. Now, meet the older brother, silicon.
Silicon is the stubborn one, the accountant.
Incredibly stubborn.
It is.
And stiff. Silicon atoms are just bigger than carbon atoms. Their electron clouds, their orbitals are more spread out.
So they prefer different kinds of structures.
They prefer rigid three-dimensional structures. Single bonds. Think of a diamond or a quartz crystal.
So carbon wants to be a flat frisbee and silicon wants to be a 3D ball or a jagged rock.
Precisely. Silicon hates forming those double bonds, and it especially hates forming flat rings with them. If you try to force 5 silicon atoms into a ring like carbon does, they usually panic.
They panic, like a cat in a bathtub.
Chemically speaking, yes. They collapse. They bunch up into a cluster because they just do not want to be flat. They snap back into that 3D rock shape because it's safer for them energetically.
So the holy grail here, what Iwamoto and his team were chasing, was forcing silicon to ignore that instinct. To be a flat ring, just like carbon's famous cyclopentadiene?
Correct. That carbon ring is one of the most important structures in all of chemistry. It's a workhorse. It's like the Phillips head screwdriver of the molecular world. So the question has always been, can we make an all-silicon version?
And for a long, long time, the answer is basically no.
The answer was more like, theoretically possible, practically impossible. People have tried. They've gotten silicon to form a double bond here and there, but a fully aromatic ring of 5 of them, that was elusive.
Now, you just said that word aromatic. The paper's title mentions a 6-aromatic C5 ring. We should pause on that because to me, aromatic means it smells like coffee. Does this ring smell like vanilla?
I would definitely not recommend sniffing it. In chemistry, aromaticity has nothing to do with smell. It's all about stability.
Well, let's break that down. This is the core concept.
So imagine a ring of atoms. In a normal bond, electrons are stuck between two specific atoms, a handshake.
Static, like cars parked in a garage.
Right. But in an aromatic ring, certain electrons, pi-electrons, are allowed to just roam free around the whole loop.
Oh, I see. So it's like cars on a racetrack.
Exactly. They run around this ring track without hitting traffic. This flow creates a ring current, and it makes the molecule incredibly stable. Carbon does this easily. It has smooth roads.
But
Silicon has potholes. Its orbitals are too big. They don't overlap well side by side, so the track is bumpy, the electrons crash, and the ring just falls apart.
So how did the team pull this off? Did they just bribe the silicon?
They used force, and they used bodyguards.
Bodyguards. Okay, are we talking Secret Service or bouncers at a club?
Think bigger. Think sumo wrestlers.
Sumo wrestlers. Okay, paint me this picture.
To keep the 5 silicon atoms in that ring shape, they attach these massive, bulky groups to each one, specifically tip groups.
Tip groups?
It stands for 2476 trispropylphenol.
Okay, yeah, let's just stick with tip. That's way easier.
Tip is much easier, and you can imagine these tip groups as giant inflatable sumo suits.
Okay, I'm visualizing it.
You've got 5 silicon atoms trying to hold hands in a circle, but they want to let go and just dogpile on each other. But because they're all wearing these giant sumo suits, the tip groups, they physically can't get close enough to dogpile.
That's a brilliant image. The suits just block them.
Exactly. It's called kinetic stabilization. You trap the molecule in the shape you want by just physically blocking all the other escape routes.
So they've got them in the suits, standing in a circle. But that's just step one. You still have to get the electrons flowing right. Turn on the racetrack.
Right, and the synthesis was fascinating. They started with a silicon chain, used a chemical called potassium tert butoxide.
Sounds like something you should not drink.
Definitely not. Then they used potassium graphite to add electrons.
Mm-hmm.
And this is where the magic happened, the real wow moment.
The visuals. Right, I saw this in the paper. The reaction actually changed color.
It did. It started as a yellow powder. As it reacted, it turned brown. And then finally, when the ring formed and the electrons started flowing, it turned purple.
Purple. Like Prince Purple Rain purple.
Or an intense orange, depending on if they use potassium or lithium. But that color change is hugely significant.
Why? Is it more than just looking cool?
Oh, it's data. In chemistry, deep colors like that often mean electrons are delocalized. They're moving freely across a large area, absorbing light.
So the purple color was basically the silicon screaming, "I'm alive! The circuit is on!"
In a manner of speaking, yes. It was the visual proof. They had built the racetrack.
So they did it. They made the silicon frisbee, they high-fived, popped the champagne. But there's a twist, isn't there? Nature doesn't give up that easily.
There is always a twist. You asked if it was a perfect frisbee like the carbon version.
Right. Carbon rings are flat, planar, like a pizza.
This silicon ring is not flat. It's puckered.
Puckered, like a Pringles chip.
A little bit, yeah. Using X-ray diffraction, which lets us see the actual position of the atoms, they saw the ring as slightly bent.
But why? I thought the sumo suits were holding it in place.
They are, but silicon is so desperate to avoid being perfectly flat that it twists just a little to relieve the tension. It's a compromise.
Okay, so it's a bent racetrack. But do the cars still go around the loop? Does the aromaticity still work?
This is the most surprising part of the paper. Yes, even though the track is bumpy, the electrons still flow.
That is wild. I would have thought the flow would break, like a train derailing.
Most chemists would have, but the data confirms it. They used NMR nuclear magnetic resonance, and they looked for a very specific signal.
Which was?
A diamagnetic ring current.
Translation for those of us who skipped that class.
It means the magnet in the machine could actually feel the magnetic field created by the electrons running in that circle. It's definitive proof. The electrons are on the track, even if the track is a little bumpy.
And what was that about a cherry on top?
Oh, the lithium atom. It's the positive ion balancing the charge. And it sits right on top of the ring, perfectly centered.
So we have a purple, puckered silicon ring wearing sumo suits with a lithium cherry on top. Now comes the big question. So what?
The so what factor, the most important part.
Yeah. It's cool science, but does it change anything for us? Is it just a trophy for the lab?
It is definitely more than a trophy. To get the value, you have to look back at the carbon version, the creep ring. It is one of the most important tools in industrial chemistry.
How so?
We use it to make catalysts, organometallic catalysts. These are the molecular machines that build our plastics, our medicines. The entire field relies heavily on that carbon ring to hold on to metals and make reactions happen.
Okay, so carbon slope is like the standard hammer in the toolbox. Everyone's got one.
Exactly. And for 100 years, we've only had the carbon hammer. Now, thanks to this team, we have a silicon hammer.
And I'm guessing a silicon hammer hits differently.
Precisely. And that's the exciting part. Because silicon is different, it's bigger, it's softer in chemical terms, this new ring will behave differently. It might hold on to metals in a new way.
So this could lead to brand new catalysts that create brand new materials.
Absolutely. New types of polymers, more efficient ways to make pharmaceuticals. If you change the tool, you change what you can build.
And what about electronics? I mean, silicon is the king of electronics. Does this play into that?
That's the other huge avenue. Because this molecule allows electrons to flow in this delocalized way, it opens up possibilities for what we call molecular electronics.
Which sounds incredibly futuristic.
It is. Think about wires or semiconductors that are the size of a single molecule. Because this ring can conduct that ring current, it could lead to whole new types of materials.
It's like we've been building with Lego bricks our whole lives, and suddenly someone handed us a new brick that's a slightly different shape and also conducts electricity.
That is a great way to put it. The authors conclude by saying this opens new research avenues that scientists speak for. We just unlocked a door, and we have no idea how big the room is on the other side.
I love that. It's the frontier.
It is. And it also blurs the line between organic chemistry, which is all about carbon, and inorganic chemistry.
An identity crisis for the elements.
In a way, yeah. It proves that the properties of an element aren't just set in stone. With the right design, like those sumo suits, you can trick them into having new personalities.
It's fake it till you make it, but at an atomic level.
I suppose it is.
Yeah.
We are coaxing nature into doing things it didn't know it could do.
All right, let's wrap this up. We've covered a lot of ground, from sumo suits to popal powders. What are the key takeaways?
I think there are three. First is that battle of nature versus nurture. Silicon wants to be a 3D rock, but the scientists nurtured it, or maybe forced it, to act like a 2D carbon ring.
Okay. Takeaway number 2, the bodyguards.
Right. None of this happens without those giant tip groups, the sumo suits protecting the ring. It shows that sometimes to make something work, you just need to prevent it from failing.
I like that. And number 3?
The puckered ring. The result was unique. It isn't flat like carbon, it's bent. But it's still aromatic, the electrons still flow.
Which proves that even if you're a little bent out of shape, you can still go with the flow.
Actually works really well.
I have my moments. You know, what really sticks with me here is that idea of impossible.
How so?
Well, you said chemists have been chasing this for decades. It was seen as maybe impossible to even isolate, but they did it.
It's a great reminder that in science, impossible usually just means we haven't figured out the right hack yet.
It makes you look at the periodic table differently. Like, we think we know who these elements are. Carbon's the party animal, silicon's the nerd. But maybe they're just playing roles.
That's the beauty of it. We're constantly rewriting the character sheets for the building blocks of the universe.
And on that note, we want to thank you for joining us in the Deep Dive Lab. If you enjoyed hearing about purple silicon and molecular sumo wrestling, please subscribe, rate us, leave a review.
It really does help us out and lets us keep bringing you these stories.
Help us float to the top of the charts like a lithium atom hovering over a silicon ring.
You're really sticking with that imagery.
I'm committed to the bit. But before we go, I have one last question for you and for the listener to chew on.
What's that?
So, we've forced silicon to act like carbon. We've rewritten its personality. It makes you wonder, if we can rewrite the rules for silicon, what other elements are out there hiding secret personalities?
That is an intriguing thought.
Could there be a germanium version of life in a lab somewhere? Could we make lead float? What else is just waiting for the right pair of sumo suits to unlock it?
Those are questions for another deep dive. But I will say, don't bet against the chemists.
I never will. Thanks for listening, everyone. Stay curious.